What if I told you that the length of a simple swinging pendulum doesn't fully decide how fast it swings, and that gravity itself is quietly controlling the rhythm, like an invisible conductor you can't see but always obey? Imagine two identical pendulums, same length, same starting angle, perfectly synchronized, but one is on Earth, and the other is on the Moon. You might expect them to behave the same way. But wait for it, they don't. And that difference reveals something deep about how our universe actually works. Picture a quiet room. A small metal bob hangs from a string, gently pulled to one side and released. It swings back and forth, steady, predictable, almost hypnotic. This is one of the oldest experiments in physics. Even centuries ago, people noticed something strange. No matter how heavy the bob was, it didn't change how long one swing took. That already feels counterintuitive. Heavier things usually behave differently, right? But here, weight doesn't matter. So what does? This is where the story gets interesting, and where the kind of thinking made famous by Richard Feynman really shines. Instead of memorizing formulas, he would ask simple but powerful questions. What is really controlling the motion? What is the pendulum actually doing at every moment? When the pendulum is pulled to one side, gravity is pulling it downward. But because it's attached to a string, it can't fall straight down. Instead, it curves, turning that downward pull into a swinging motion. At the very top of its swing, it's momentarily still. Then gravity pulls it down, speeding it up. At the bottom, it's moving fastest. Then it climbs back up, slowing down again, until it stops, and repeats the whole cycle. Now here's the key idea: the time it takes for one full swing, what physicists call the period, depends on how strongly gravity is pulling it back toward the center. Stronger gravity means a stronger pull, faster acceleration, and a quicker swing. Weaker gravity means a gentler pull, slower acceleration, and a longer swing. Let's go back to our thought experiment. On Earth, gravity has a certain strength. On the Moon, gravity is about 1/6 as strong. So what happens? The pendulum on the Moon still swings, but it moves more slowly. Each swing takes longer. It feels almost like time itself has stretched. And here's the fascinating part: nothing about the pendulum itself changed. Same string, same mass, same starting point. The only difference is the environment, the gravitational field it's in. It's like the pendulum is listening to gravity and adjusting its rhythm accordingly. This idea leads to a deeper realization. The period of a pendulum isn't just about the object, it's about the relationship between the object and the planet it's on. Gravity becomes part of the system, not just a background force. Feynman loved this kind of insight because it reveals a pattern hidden beneath the surface. Instead of thinking, a pendulum swings like this because that's just what it does, we start to see the underlying rule: the swing is a conversation between motion and gravity. Now imagine you're designing a clock using a pendulum. For centuries, that's exactly what people did. Pendulum clocks were incredibly accurate, but only if they stayed in the same place. Move that clock to a mountain where gravity is slightly weaker, and suddenly it runs a little slow. Bring it back down to sea level, and it speeds up again. Tiny differences, but measurable. So in a way, every pendulum clock is secretly measuring gravity. It's not just telling time, it's responding to the Earth itself. Let's push this idea even further. Suppose you could take a pendulum to Jupiter, where gravity is much stronger than on Earth. What would happen? The pendulum would snap back faster, completing each swing more quickly. Time, as measured by that pendulum, would feel compressed. Same object, completely different behavior, just because gravity changed. This leads to a beautiful and slightly mind-bending thought: the rhythm of motion we observe isn't fixed. It depends on where you are in the universe. The laws are the same everywhere, but their effects play out differently depending on the environment. Feynman often emphasized that physics isn't about memorizing results, it's about understanding relationships. And the pendulum is a perfect example. It's simple enough to visualize, but rich enough to reveal something fundamental: motion is shaped by forces, and forces are shaped by the universe around us. Now, you might wonder, does the angle you release the pendulum from matter? If you pull it back farther, does it take longer to swing? Surprisingly, for small angles, it doesn't change much at all. The period stays almost the same. That's why pendulums are so reliable for timekeeping. But if you pull it back really far, things start to change. The motion becomes less predictable, and the timing shifts slightly. It's a reminder that even simple systems have layers of complexity waiting to be discovered. But let's come back to gravity, because that's where the real story is. Gravity isn't just pulling objects down, it's shaping motion in a very precise way. It determines how quickly something accelerates, how energy is exchanged between height and speed, and ultimately, how long a cycle takes. Think of it like music. The pendulum is playing a note, over and over again. Gravity sets the tempo. Change the gravity, and you change the beat. The same note, the same instrument, but a completely different rhythm. And here's where it gets even more interesting. If you didn't know the value of gravity on a planet, you could measure it using a pendulum. Just time how long it takes to swing, and you can work backward to figure out how strong gravity is there. In other words, a simple swinging object becomes a tool for probing the nature of a planet. That's the kind of elegance Feynman admired. Complex truths emerging from simple observations. A string, a weight, and a question: why does it swing the way it does? Now step back for a moment and think about what this really means. Every time you see something swing, a playground swing, a hanging lamp, even a metronome ticking on a piano, you're witnessing gravity in action, shaping motion in a precise and predictable way. It's easy to overlook because it feels so ordinary. But hidden inside that ordinary motion is a deep connection to the structure of the universe. And that's the beauty of physics. It takes something familiar and reveals the invisible rules behind it. It turns a simple swing into a story about forces, motion, and the nature of reality itself. So the next time you see a pendulum, don't just watch it move. Ask yourself what's really controlling that motion. Think about how it would behave on another planet, under a different sky, with a different pull of gravity. Imagine the rhythm changing, the timing shifting, the entire motion subtly transformed. Because in that quiet, repetitive swing, there's a conversation happening between the object and the universe. And once you start to hear it, you realize it was there all along. If this made you see something ordinary in a completely new way, hit like, subscribe, and let me know in the comments what everyday phenomenon you want to explore next. Because sometimes, the biggest mysteries aren't hidden in distant galaxies, they are right in front of us, moving back and forth, waiting for us to notice.